Momentum is a fascinating concept in physics that bridges the gap between motion and mass. This lesson will introduce you to the fundamental idea of momentum, helping you understand how it plays a crucial role in defining the movement of an object. Before we dive into detailed calculations, let's grasp the essence of momentum and how it can be visualized in everyday scenarios. Imagine a bus barreling down a highway. What makes it so hard to stop? The answer lies in its momentum, a combination of its mass and velocity. Momentum is a fundamental concept in physics describing the motion of an object. Let's break it down. Momentum is the product of a mass and its velocity. This relationship is crucial in understanding how objects move and interact. We represent momentum with the symbol letter P. The equation for momentum is straightforward. P is equal to mv, which m stands for the mass and v represents its velocity. The unit of measurement for momentum is kilograms meter per second. Remember, momentum helps us predict and analyze the motion of objects, which is essential for solving various real-world problems. In the next slide, we'll explore examples to see how this equation comes to life in practical scenarios. Example number 1. Let's consider a 2,500 kilogram bus traveling at 25 meters per second along South Superhighway. The question here is, what is the momentum of the bus? First, let's identify what we have. We are given 2,500 kilograms of mass, and the velocity of the bus is 25 meters per second. We are required to find the momentum. The equation to use is P is equal to mv. Now, let's substitute the given values. The mass is equal to 2,500 kilograms, and the velocity is 25 meters per second. We multiply the two quantities. Then we will have 62,500 kilograms meter per second as the momentum. This example highlights how momentum is calculated and sets the stage for our next problem, where we'll explore how the momentum of this bus can be compared with a car. Example number 2. Here, we want to find out how fast an 1,800 kilogram car must travel to achieve the same momentum as the bus from our previous example. Let's break down the solution. We know the car's mass is 1,800 kilograms, and the target momentum is 62,500 kilograms meter per second. By using the equation P is equal to mv, we can rearrange it to solve for the velocity. Then we have a working equation V is equal to P over m. Substituting the values, we divide the momentum by the mass. So we have 62,500 kilograms meter per second divided by 1,800 kilograms. This calculation shows that the car needs to move at 34.72 meters per second to match the bus's momentum. This example illustrates how changing mass and velocity can produce the same momentum, reinforcing the relationship between these variables. We note that as the momentum increases, the velocity also increases. The velocity and momentum are directly proportional. Moving on. Conservation of momentum is a fundamental principle in physics. It states that the total momentum of a closed system remains constant, provided no external forces are acting on it. This principle is crucial for understanding how objects interact and move. Think of it like this. When two ice skaters push off each other, they move in opposite directions. Yet, the total momentum of two skaters before and after they push off remains the same, assuming no external influences like friction. The concept of momentum conservation help us analyze a wide range of physical phenomena, from simple collisions to the complex dynamics of celestial objects. The law of conservation of momentum is a principle that can be visualized as a balance where the momentum before any event must equal to the momentum after, provided no external influences interfere. This means that while the individual momentum of each object may change during a collision, the total momentum remains constant unless an external force is applied. Understanding the principle of conservation of momentum is crucial in this lesson. It is crucial in physics, especially when we consider how objects interact. At the heart of this principle is Newton's third law of motion, which tells us that for every action, there is an equal but opposite reaction. When two objects interact, they exert forces on each other that are equal in magnitude but opposite in direction. This means that the total momentum before and after their interaction remains constant, provided no external forces act on them. This principle is fundamental because it helps us predict the outcomes of interactions such as collisions in a system. By understanding this, we can analyze and anticipate the motion of objects in various scenarios, from simple experiments to complex real-world applications. Here, we're going to dwell deeper into the mathematical expression of the conservation of momentum for an isolated system. First, let's break down the equation. m1 v1 plus m2 v2 is equal to m1 prime v1 prime plus m2 prime v2 prime. This represents the momentum before and after the interaction of two bodies. The left side of the equation reflects the initial momentum, while the right side shows the momentum after the interaction. Here, m stands for mass and v signifies velocity. These are the core elements that determine the momentum of an object, which is measured in kilograms meter per second. Remember, the law states that the total momentum before the collision is equal to the total momentum after, provided no external forces act on the system. This principle is crucial in understanding how momentum is conserved in collisions. which we'll explore further in the next discussion. Collisions are fascinating interactions that occur when two or more objects come in contact with each other. These interactions are governed by the law of interaction, which tells us that during a collision, the objects involved exert forces on each other that are equal in magnitude and opposite in direction. This is a direct application of the Newton's third law of motion. Understanding this principle is crucial because it sets the stage for analyzing how objects behave during collisions. Whether it's a car crash, a game of pool, or even particles colliding in a particle accelerator. As we move forward, we'll explore the different types of collisions and what is conserved in each scenario. This will help us gain deeper insights into the dynamics of these interactions. Elastic collisions and inelastic collisions are two fundamental types of collisions in physics. Let's break down their key characteristics to understand how they differ from one another. First, elastic collisions. In an elastic collision, both momentum and kinetic energy are conserved. This means that after the collision, the total momentum and the total kinetic energy of the system remain the same as they were before the collision. Imagine two billiard balls striking each other and bouncing off. They are a classic example of an elastic collision. On the other hand, inelastic collisions involve the conservation of momentum only. Kinetic energy is not conserved because some of it is transformed into other forms of energy, like thermal or sound. In a completely inelastic collision, the colliding objects stick together after impact, moving as a single mass. It's crucial to understand these differences because they help us predict the outcome of real world collisions, whether in car accidents, sports, or molecular interactions. Now, as we move on to the specifics of elastic collisions, keep these fundamental concepts in mind. They are integral to analyzing how objects behave during different types of impacts. We're focusing now on elastic collisions, a fascinating concept in physics where the objects involved separate after impact. The key takeaway here is that two important quantities are conserved: kinetic energy and momentum. This means that the total amount of motion and energy before and after the collision remains the same, even though the motion of an object or individual objects may change. Imagine it like perfectly choreographed dance where each dancer maintains their energy and momentum, even as they interact and separate. Now, let us visualize this process. Before the collision, we have objects A and B with initial velocities and masses. After the collision, they move apart with different velocities, but the same combined energy and momentum. This conservation is hallmark of elastic collisions and is crucial in understanding many natural and technological processes. Let's move on to explore more nuances of elastic collision and how they differ from inelastic ones. Let's start by understanding what perfectly elastic collisions entails. In an ideal situation, a perfectly elastic collision allows one body to completely transfer its momentum to another. However, in the real world, we typically encounter nearly elastic collisions. This means that while the principles of momentum transfer are still in play, not all energy is perfectly conserved due to external factors. Now, a critical point to note is when the masses of the colliding objects are unequal. Their velocities must adjust to maintain constant total kinetic energy. This ensures the sum of kinetic energy before and after collision remains the same. Understanding these principles help us predict and analyze the behavior of the objects after collisions, which is crucial in fields ranging from engineering to sports science. Unlike elastic collisions, where both kinetic energy and momentum are conserved, in inelastic collisions, only the momentum is conserved. This means that while the momentum of the system remains constant, some kinetic energy is lost or transformed into another form of energy, such as thermal or sound. A key point to highlight is that in some inelastic collisions, the objects may stick together after impact, leading to them moving as a single entity. This distinct form elastic collisions, where objects always separate after impact. By understanding these fundamental differences, we gain insight into how energy and momentum interact in various collision scenarios. When discussing perfectly inelastic collisions, it's essential to understand that these are collisions where the objects involved stick together after impact. This scenario results in the two objects moving as a single entity with a shared velocity. What's crucial here is that while momentum is conserved, kinetic energy is not. This energy loss is typically converted into other forms such as thermal or sound. Momentum is conserved and not kinetic energy. Visualize this. With the diagram on the slide before the collision, each object has its velocity. After they share a common velocity, this change signifies the transfer of momentum and transformation of energy. Understanding these principles is key as we'll explore practical example involving billiard ball. Let's dive into this example of a collision involving a cue ball and a three ball, both with a mass of 170 grams. First, we're looking to determine the total momentum of the system before the collision. Remember, momentum is the product of mass and velocity. Given that both balls have equal mass and the three ball is initially at rest, we focus on the cue ball's momentum, since the cue ball is the one moving. Now, even though the cue ball stops immediately after the collision, the total momentum before and after the collision should remain the same if the system is closed and isolated. Our task is to provide or to prove that this is a conservation of momentum through calculations. So let's have the solution. Firstly, we need to remember that momentum is denoted as the total momentum or P sub t. This is the product of mass and velocity. In this case, we have two objects, the cue ball and the tree ball. The cue ball is moving towards the tree ball, which is initially at rest. To calculate the total momentum, we use the formula m1 v1 plus m2 v2 is equal to your pt. Given that the mass of each ball is 0.1700 kilogram and the initial speed of the cue ball is 4 meters per second, the equation becomes pt is equal to 0.1700 kilogram times 4 meters per second plus 0.1700 kilogram times 0. Since the tree ball is at rest, the initial momentum is now equal to 0. So we now multiply the momentum of the cue ball, which is now equal to 0.68 kilogram meter per second. We need to note that this value represents the system's momentum just before the collision. Now, to prove whether our answer is correct, first, let's address the key idea. The momentum before and after collision remains the same, which is a fundamental principle in physics. We began with the cue ball moving at 4 meters per second and the tree ball is at rest. After the collision, the cue ball stops, indicating its velocity, transferred entirely to the tree ball. This is why we see equation m1 v1 plus m2 v2 is equal to m1 prime v1 prime plus m2 v2 prime. The equation signifies since initially the tree ball had no momentum. The transition of velocity from the cue ball to the tree ball is captured as m1 v1 minus v1 prime is equal to m2 v2. This shows that the velocity of the tree ball equals 4 meters per second, while the cue ball's final velocity is 0. Let us remember that the system's momentum is conserved perfectly. The velocity transfer underscores how energy moves within isolated systems without loss. This example clearly illustrates the fundamental concept of momentum conservation in physics. So that is momentum and conservation of momentum. Thank you for listening. I hope you learned something.